we can actually make it much better, because coq has a mechanism, LTAC has a mechanism for doing pattern matching on the goal and using that to apply tactics in a smarter way. And so this is an example. Using this match goal construct is like the first entry point into getting your own sort of hyper automation when you're writing your own LTAC code. Because here we can actually build LTAC that will do different things in different cases and is capable of adapting to the goal as it exists in the set of assumptions you have. So this is a really simple example of that. So let's see how this works. So this match goal construct it's a little bit confusing because it has the same pattern as the match construct in Galena when you're doing pattern matching on inductive data types. And indeed, we are doing pattern matching here, but it doesn't have the same set of rules, not rules, but restrictions as pattern matching on inductive data types. So for starters, match goal with blah doesn't need to be total. We don't need to have a complete accounting for all possible goals, and there doesn't need to be a default case, okay? In the case that there isn't a matching goal, this match statement is going to fail, but that's okay. We'll see how to deal with that in a second. Okay, so let's consider this match goal statement. Here's the form. So we're just going to say match goal. Goal, as you can imagine, just this magical LTAC piece of syntax that's meant to evoke standard pattern matching. So here we're going to say match some hypothesis. We're naming the hypothesis here, so we could have put, this is a pattern variable that we will use in the body of this clause right here. And then we put the colon, and then we're going to say match any hypothesis that has this form. So here we're going to have a meta variable, question mark E, that stands for anything. And it says, okay, so I want you to find a goal. If the goal has a hypothesis of the form something equals true, and then we have another hypothesis that is of the form that same thing equals false, then I want you to use this custom bit of tactic we had before to invoke that tactic with this hypothesis as the first argument and this hypothesis as the second argument. Okay. Now this little bit is also required. This allows you to pattern match on the goal itself. So here are the assumptions. They come before this turnstile. And you can also pattern match on the goal with the stuff that comes after the turnstile. Because here we don't care about what was in the goal. We're just going to leave an underscore. It stands for don't care. Okay. It's also important to note that now we have these nonlinear patterns. And what do I mean by that? So this will only match a goal state where you have the same thing on the left-hand side of both of the equations. And you can't do this in a normal pattern match in Galena, right? You have to have fresh pattern names or you'll get an error if you try and replicate them. Right. So are there any questions about this construct or should we see it in action? Yeah. So the question is, this H1, H2 required, and are they just names? So the answer is yes, they are just names. We could have called this foo if we'd wanted, or bar, or H3, and just as long, they're just the identifier we're going to use to refer to them in the body of this clause. Yeah. Yep.
So, like we are saying that if one hypothesis is true and the other one is false, then.
Yes. Okay. Right. So if you recall from the definition of this rewrite inv tactic, it's going to try and rewrite H1 in H2. And so if they're not the same, this tactic will fail. Yeah. Yes, next question.
What is the meaning of the question mark?
So what is the meaning of the question mark? So in this LTAC match goal statement, we refer to the variables that we're matching against. We put a question mark before them to specify that they're variables and not identifiers. So if we left this question mark off, it would literally be looking for the constant E at that position, as opposed to interpreting it as a pattern variable.
Since E is not used, could you use question mark underbar?
I don't think question mark underbar is well formed. You could have just put an underbar there. The issue is now if you put underscore in both of these places, it would match, and it wouldn't consider, it would also match goals where you have assumptions with different things on the left-hand side of these two equations. So if we had x here and y here, it would still match that because we're not forcing them to be the same. Does that track? Now, yeah. Yes, another question.
And you can also match terms, right? Not just variables. Any term?
This E, the question was, can this E match any term?
Yeah.
And the answer is yes. This is yeah. This will match anything that appears on the left-hand side of an equation.
And the E's have to be equivalent.
And in this case, when you say equivalent, the E's have to be syntactically equal. They have to have the exact same. They have to be the exact same expression. Okay. Any other questions? Okay. Let's now see this tactic in action. So now what we're going to do is, okay, recall I said before that this pattern match could fail. It could fail for a lot of different reasons. So it could fail to match the goal. So if there are no clauses in this match thing, match goal, this will cause coq to return an error. It will say this, I couldn't find any matching pattern. There were no matching clauses for this particular pattern, and it'll fail, and it'll cause your tactic to mess up. But we can handle the case where tactics fail, right? We have this try tactical we saw last time. So we're just going to wrap the invocation of this tactic down here in try, and it's going to try and solve every sub-goal it can using this magic tactic we just defined. And indeed, it can solve 3 more goals just by putting that try there. And that's great. If we don't put it there, I think what we'll get is a grumpy error. It says no matching clause for match. But we don't want to do that, so great. So cool. We've built this little custom bit of LPAC magic using this match statement that resolves some of these cases automatically. And what is so pleasant here is that this match statement, because we get to define our own, we're matching against the assumption names. If for some reason, coq decided to give different names to the assumptions when we use intro, or we changed E1 to E1 prime or something here, this tactic will still work because it's using this pattern matching syntax. It's sort of indifferent to the concrete name we've chosen to give to these assumptions. It's going to figure that out for us. So in that sense, it's much more adaptable than, say, your standard way of maybe hard coding the names of assumptions in your proof script. That's sort of a fine point that might become apparent with more usage of coq. Okay, so there's that example. Right, so the remaining cases. So let's look at the remaining cases. We're down to almost all of the cases being solved by one tactic. Let's look at what else is left. Yes, I'm sorry. Yes, question.
I have a quick question just about the match. Is it possible, instead of using try, to add a second case that would match something else and then just do nothing?
Yeah, so we can do that. The question is, could we add a second case so we don't even have to use the try? It'll be a case that does nothing. And the answer is yes. And oops, I will go ahead and just show you how to do that because it might be useful in the future. So here we can create a new clause, as you might expect. In this case, we'll use the bar. It'll say, we're just going to match any goal. And what do we want to do in that case? Well, it turns out there's a tactic called ID-tac, which stands for, I guess, the identity tactic. And that is the tactic that always succeeds and does nothing to the goal. So it's sort of the no-op tactic. And if we stick that in there as sort of the default case, everything works fine. Okay, so I guess it's worth noting, getting a little bit into the semantics of how this match statement works. So the way this works, this LPAC match statement works, is if you have a clause that matches if a clause doesn't match the goal you have in hand, or if a pattern doesn't match the goal you have in hand, it proceeds to the next one. Okay, suppose it did match the goal that you have in hand, and then it's going to try the tactic that follows it, right? If that tactic succeeds, it's done. If it fails, then it proceeds to the next clause. Does that make sense? So if we had written, we could actually, yeah, that's all I'm going to say about that. Yeah. So you can imagine you can actually build some sort of implicit backtracking in these match statements by trying different tactics, and sort of it'll back up in clause order, and it'll back up to the next clause and work its way down. So there's a lot of power you can add to your search by using this match statement.
Can I ask a specific question?
Yes.
I'm confused about like there is a comma after like H1, but then after H2 there is like how to.
Yeah. So there's a question. Yes. There's a question about the syntax. Why do we follow H1 here with a comma? That's just how you separate the list of different assumptions, right? And because H2 is at the end, it's followed by this turnstile thing, so it knows that's the last assumption that's in the pattern.
And turnstile is the goal, like the below the line.
Yeah, the thing after the turnstile, oh yeah, here, that's the goal. That pattern matches on the goal. Okay. Are there any other questions? Yeah, sure.
Can we pattern match on a subpart of the goal?
The question was, can we pattern match on a subpart of the goal? The answer is yes. There is syntax for that. But I want to press through the rest of this chapter, and we can revisit it at the end. You can ask me about that, and I'll show you the syntax for it. Yeah, yep. But you can do a lot of stuff with this match construct. Okay. Okay, right. So moving on to dealing with the rest of these cases. Okay. So here are the remaining cases. Before we were asserting something and we were applying one of the induction hypotheses to it and doing some rewriting to solve that the goal we asserted and then rewrite with that. Well, we could have just rewrote with the fully applied inductive hypothesis, fully apply these inductive hypotheses and rewrite with them right away, which is what we do on this next slide. So it's a bit of an adaptation. Not too important. The reason we did that is that now we can reuse this LTAC match goal statement to automate this process as well. So here's another example of the match goal statement in action. So what is this one going to do? Well, it's going to look at the goal you have in hand that you invoke this LTAC on, this tactic on, and it's going to look for an assumption of the form for all x, some property p of some predicate applied to x. So p satisfies some property. I don't know what it is, and it's going to imply some equality. And then it's going to look for a second hypothesis that has the form p applied to something, right? And what is it going to do? Well, it's going to try and rewrite using this assumption, using the concrete x that this assumption was applied to, and satisfying this part of the implication of this rewrite rule with this second hypothesis. I guess I could describe this in English a little bit more, but if you look at the code, hopefully it sort of sinks in. So there is one thing to note about this. These lists of hypotheses that you're pattern matching against, there's no ordering really going on here. You can imagine that what this match statement is going to do is it's going to go through the assumptions you have in hand and try and find one that matches the first one, and then it will start over and try and find one that matches the second one. So there could be additional assumptions between them. H2 could appear before H1. In theory, it doesn't matter. This will just adapt to that and pattern match on it as you would expect, which is pretty nice. Yes, question?
So how does it match the connection between the capitalized
The question was, how does it match the the capital X and the lowercase x.
That's what saying that the capitalized X is like this.
Yeah. When I was an instance. So if you look at the first assumption here, H1 is what we're calling it, it has this universal quantifier, so it's quantifying over all possible x's that could have this, it's a universal quantifier, right? And H2 has this concrete one. And so in order to fully apply H1 to get the conclusion, we need to supply it with a concrete x and then proof that x satisfies this condition P, right? And that's what's going on here. I don't know if that answers your question properly. Yeah. I guess it's, well, no, I don't want to dig into that a little bit more. Yes, there's questions. Go ahead.
So that matching for the universal quantification,
Yes.
is it done up to alpha conversion?
Oh, yes. So the question was, is this pattern match against, on this universal quantifier, is it done up to alpha equivalence? And for those of you who don't, another way to state that is, does the pattern matching depend on the concrete identifier used here? Does it need to be X? The answer is no. It could match a goal, an assumption that had the form for all Y or for all Z. Doesn't care. So alpha, the naming is irrelevant here. There's another question. Yep.
All I was going to say is in response to that question before, is the act of applying x to A1, giving it the concrete x to slot into that for all x.
Yes.
And then giving H2 to that fills in the hypothesis.
Yes. Yes, that's right. Let me give you a concrete example of it in action. So, okay, I'll just note first of all that now that we have this tactic in hand, well, we can just add this custom tactic we wrote to the end of this. We'll just semicolon it on to the end of our proof script, and it's just going to solve this our original proof. And people often call this like a one-liner to imply that it's just a single line of proof script. Although obviously, A, it has more than one line, obviously, and B, it has more than one piece of LTAC in it. And on top of that, these LTACs we defined had had a bunch of sub-tactics that they were calling. The fact remains that this is a one-liner because it effectively discharges the goal in one single LTAC, piece of LTAC, one-liner. And this is sort of the gold standard in automation for a reason we'll see in a second. So now I want to try and adjust that question a little bit more with this find equation tactic. So one of the cool things about this find equation tactic is we'll notice that we're quantifying, this is actually very general, right? So we're quantifying over any sort of assumption that could be made here. This could be any property P, and any sort of equality. It doesn't matter what's on the left-hand side or the right-hand side. This could be an equality between natural numbers. It could be an equality between strings. It could be an equality between who knows what, right? And so we can actually apply this find equation tactic in many different goals. So as an example, if we had something, find x, I'm doing this on the fly, so let's see. What's a good one? For all x, y, z, if it is, okay, yeah. If we had for all, let's say q, where q is less than or equal to y implies x equals z. Okay, and then we'll say that we'll have m is less than or equal to y as an assumption, and then we will try and prove that z equals x. Okay, this is type, oh, right. Okay. So now I'm going to have to intros, and if I do a find equation, oh, it didn't work.